Good afternoon. My name is Alex Canny. I'm with Preferred Utilities, and today we're going to be talking about fuel oil quality management for emergency power systems. We're going to start with an introduction for myself and the company, and I know a lot of you have been probably following our webinars along the way, so it'll be a bit of a review. We're going to be talking about how specifically tank design impacts fuel oil quality in the following section, because most of the fuel spends most of its life in tanks, whether it's a bulk storage tank, sub-base tank, day tank, etc. And then in the final section, we're going to take a closer look at the factors that affect fuel oil quality. We'll be looking at exactly what's happening in those tanks to the fuel itself. So starting off with an introduction, Preferred Utilities has been operating continuously since 1920. We have over 180 years of combined engineering experience, and that's probably a low estimate at this point. Our headquarters and factory are located in Danbury, Connecticut, but I am located in Manchester, New Hampshire, and we have offices all over the country. A lot of what we're going to be talking about today will be applicable across the country. The specifics as far as regional issues that may come up will be local to Boston and the Northeast, but there's a lot of places around the company that have special requirements, such as New York City, California, and we have other webinars and other resources and local offices that can help you out for anything that's specific to a region or a city across the country. We are experts in mission critical facilities, so you will run into our equipment in different facilities such as schools and things like that. But where our expertise really shines is in things like healthcare, data centers, facilities that really can't go down. And today we're going to be talking about specifically backup power fueling systems. We do a lot of work in boiler plants with biofuels and things like that. But today specifically we're going to be talking about maintaining the quality of fuel for backup power generator systems at these mission critical facilities. I always like to start with a quick review of what a traditional fuel oil system is to kind of ground ourselves for the talk. And I know a lot of people don't do this sort of work all the time, so it can be very helpful to have a brief review. Here we have an example diagram of a traditional centralized fuel supply system. We have on the lower left, starting with how the fuel enters the system via delivery, we have our bulk storage tank. And in this case, it's shown outside the building envelope and underground. As we move throughout the system, you'll notice in the center there we have our duplex transfer fuel skid. That's also traditionally where the bulk of the controls for the system will be located. And then as we move vertically, we have our fuel going up to the upper level to a local storage day tank at the emergency generator. Off to the right, we have our fuel polishing skid, which is going to feature prominently in this presentation as we are talking specifically about fuel oil quality management. And this is typically how a system would be laid out. Now, the bulk storage tank that we're going to spend some time on, this could be located above ground. It could be inside the building envelope rather than outside. And we're going to take a look at how those decisions of where to place the tank and even how to design the tank itself are going to affect the long-term quality of the fuel. So jumping right into tank design, how does this impact fuel oil quality? And why does tank design matter? I know a lot of times it may seem that the fuel is going to do what it's going to do. It doesn't matter the size or shape of the tank that it's in or the materials, but really the fuel health is in many ways tied to the health of the tank that it sits in. Just on the surface, if the tank corrodes or is punctured, the fuel is affected. We have moisture that could enter the tank, things like that. And the reason that we're going to take the time to talk about this so much is that the tank itself is something that can be controlled directly at the design phase. So there are many operational things that can help the quality of the fuel, but those can't necessarily be controlled at the design phase. We can't control whether or not somebody has a service come in to test the fuel 10 years down the road, but we can control the system as it is designed, and especially relating to the main tank. Now, I want to take a moment to talk about one of the trends that we're seeing in the industry, and it affects really the way that we've introduced this topic, and that's standalone versus centralized fuel storage. So in the first slide that we looked at with the traditional fuel system, That was a centralized system. We had a bulk storage tank that serves one or more smaller tanks located at the generators. Now, a type of system that we're seeing a little more of, especially in applications like data centers, and typically when they have plenty of room outside the building, are a standalone configuration for emergency power generators. So some advantages of this, where we have a larger subbase tank located directly under the generator, is that, I mean, quite obviously, we have more fuel stored at the generator. So we don't have to worry about things like transferring the fuel. If we have a situation where a transfer pump was to go down, we don't have to worry about the limited amount of fuel stored in a belly tank or a day tank. All of the fuel is located at the generator itself. Now, again, this is usually limited in a city or something like that where real estate is at a premium. You're typically not going to see this because it usually requires the generator to be located out on the lawn or next to a building with the large tank under it. And fuel would typically be delivered directly to this tank by the delivery service. Now, what are the drawbacks of this setup? Well, if we have, let's say, multiple generators sitting out on a lawn with storage directly underneath them, we don't have the ability to circulate out the fuel and change it out. There are many cases where we can have a condition on the fuel such as temperature, water content, things like that. And if we have a centralized fueling system, we're able to swap that fuel out immediately without necessarily having to remedy the problem at hand. Also allows us to fully test the level sensors. So if we have smaller day tanks and a larger main tank, we can use a return pump on that to draw the level down and test all of the level points on the tank that's at the generator. In the case of a standalone system, we don't have the ability to do that without actually burning off the fuel or removing it manually somehow. Also, the ability to circulate it and move it around in a centralized system is going to greatly ease fuel maintenance. In a standalone system, we're pretty much requiring somebody to have a service come out and circulate the fuel to a truck or other mobile device to remove water and polish the fuel. And again, that's something that we can't control 5 or 10 years down the road. So what we can control at the design phase is a centralized system with a dedicated fuel polishing system and a way to circulate that fuel back to the main tank so that we can maintain the quality of the bulk fuel. Another issue is fuel redundancy. So when we have a standalone system, if we have 4 generators sitting out there, and let's say each one has 1,000 gallons each, and we lose one engine, we don't have the total runtime of that fuel anymore because there's now 1,000 gallons that's captive to the engine that is no longer operational. So in this case, even though we may have redundancy as far as energy output, we don't necessarily have redundancy as far as total amount of fuel stored in the system. In a centralized system, if one generator has an issue on the engine, we can remove the fuel located at that local tank with a return pump, or if there isn't a return pump, typically the amount of fuel stored at that location is going to be much smaller and less of an impact on the total redundancy of the system. Now, of course, underlying all of this with a centralized system, there is some additional complexity. And there are a lot of different things and different issues we're going to have to take a look at to make that work differently than a standalone system. But those are some of the differences between the two. Now, focusing on the centralized fuel storage system, one of the first things that has to be decided on when designing this system is where is the tank going to be located? Is it going to be above ground, underground, or vaulted? Now, these decisions really come down to 2 different types of tanks that we're going to design. Whether the tank is above ground, underground, or vaulted, it's either typically going to be a direct burial tank or it's going to be an above ground tank. So even if we are in a vaulted situation where the tank is in a basement or some other sort of contained area, the design of the tank itself is going to be very similar to an above ground tank, with maybe the exception for the need for UV protection. Now, taking a look at a comparison for underground versus above ground tanks. With an underground tank, you're going to be more thermally stable. And this could be a big impact depending on where the system is located. If we're in the north, where cold can be an issue, or in the south, where heat can be an issue, this may be a big way to control that. Having a large amount of thermally stable fuel underground and the ability to recirculate fuel from an area that's potentially too hot or too cold back to that. Also, underground, of course, there's no UV protection requirements. And as far as protecting it from impacts, it's very hard to hit a tank with a car if it's underground. So a bit of an advantage there. Some of the disadvantages are that it can be harder to inspect. And again, we're talking about direct burial tank. So if this thing is backfilled and located underground with just a few access points, it is going to be harder to physically look at the outer shell of the tank because it's buried. It can also require more complicated leak detection. I've seen a lot of systems where they have monitoring in the soil itself for hydrocarbons. Rather than a dry interstitial space on a double wall tank, you may have a brine-filled system where we're now measuring changes in level of the brine. A lot of different ways to do that. For an above ground tank, typically leak detection is going to be a dry interstitial space that's monitored, possibly with some additional monitoring within a diked in area or within the basement area if that's inside the building envelope. Now, if we're above ground and outside the building, the tank may need to be insulated, talking about some of those thermal issues that we mentioned earlier, and it may need some impact protection, but it's going to give you an easier ability to inspect the outside of the tank. And one of the big differences between the two is that the above ground tank can offer a lower initial installed cost. And that's not necessarily the cost of the tank and accessories, that's the total cost for the installation and everything. Because typically the amount of excavation and backfilling that's going to be required for an underground tank is going to push that total cost above what an above ground tank would be. Now, one final consideration on the above ground tank is that it may need to be fire rated. So if you're in a situation where that could be an impact, whereas underground, obviously fire is not going to be as much of an impact on a tank. Above ground, that could be the case. And there are options out there for tanks that have insulation in the interstitial space or externally as well. Now, let's take a look at the materials of construction. So for above ground tanks, typically we're going to see steel employed, such as a UL 142 double wall tank. Underground, it's very common to see fiberglass, whether it's double wall fiberglass or more of a hybrid. And another above ground design that we see quite a bit is concrete. So you may see for smaller applications such as fleet fueling in a small maintenance area, you may see a rectangular concrete tank above ground. We don't deal with those quite as much as those are a bit more specialized, and those can have their own issues. We've run into some issues with those, especially if they have the exposed concrete on the outside with a rectangular design where the flat top, and here in the Northeast with the weather changes and the freezing in the wintertime, you can get situations where that concrete will develop micro cracks and have water infiltration into the secondary space. So the two that we're really going to focus on that are the most common for mission critical applications are going to be carbon steel and fiberglass. Taking a look at another comparison here, carbon steel is applicable for underground or above ground. Some of the advantages of carbon steel is the compatibility with fuels and additives. We're going to talk a little bit more about that in a bit, some of the compatibility differences between these two materials. Now, historically, carbon steel tanks would need a coating or some sort of cathodic protection, and they're typically going to be structurally stronger with a smaller footprint. So a fiberglass tank may need larger reinforcing ribs on the tank itself, a little bit larger footprint for structural integrity. Now for fiberglass, especially if we're talking pure fiberglass double wall, that's going to be underground only. We typically won't see these above ground because they're just not structurally designed for that. Now, obviously, an advantage of that is that they can be lighter for transportation. But there are multiple resin formulas. As I mentioned, we're going to talk a bit more about that and how that affects compatibility. Of course, there is no cathodic protection needed or consideration for coating because fiberglass is not going to react with its environment that way. Another comparison note here is that fiberglass can also have a larger interstitial space, and that can impact how quickly the fuel will migrate to any sort of leak detection versus carbon steel, which may be one of the reasons that we see a brine-filled system employed more often than a dry interstitial space for fiberglass tanks. So speaking of compatibility, it's important to understand that fuel has many different additives in it, and those can change over time. And so the total compatibility of a fuel with its tank material can also change. There are many different ways that this is accommodated, but one thing that we know is that in the fuel industry, the transportation containers and the production equipment all uses carbon steel. So as far as the additives that are going to be affecting carbon steel, that's going to be severely limited just because of how the supply chain is set up. For fiberglass, though, there are actually multiple resin formulas that manufacturers will have on hand, and they will change over time to accommodate the ethanol, sulfur, isobutanol, and other additives and content within the fuel. And some of the dangers there, if we have a system where we have a reaction with some of the additives that are in the fuel, we can have things like internal delamination and blistering. And it's important to understand that that is the way that the fuel can possibly interact with the resin. So obviously in fiberglass, the glass itself is fairly inert. But if we have a resin formula that was designed for a certain composition of fuel 10, 20 years ago, and those additives change, there's a potential for impacts down the road. Now, of course, with carbon steel tanks, we know that they pose their own challenges. If we have water content and things like that internally on the tank, that can pose its own corrosion potential there. So one of the ways to combat that is with tank lining. And this is an option for carbon tanks to increase longevity. It allows easier cleaning and inspection, and it's usually about a 20% cost adder over an unlined tank. And considerations like this are more important, especially because we're seeing a larger amount of fuel stored and a lower consumption rate overall. We have a lot of different impacts in the industry, especially facilities where they may have used a larger amount of fuel because the tank was also associated with a boiler plant that was burning liquid fuels. Many of these plants now are converted over to gas or an alternative fuel, and so the total amount of fuel being burned is much lower compared to previously. So you're seeing a longer storage time on these. So ways to minimize these impacts are going to be even more important over time, as well as sulfur content. We see a lot of systems that maybe over the years were marginal on their fuel oil quality, but now that the sulfur content has been lowered in the fuel, we see a higher impact on fuel degradation. And we're going to talk a little bit more about the fuel itself in a later section. So as far as tank external coatings, when it comes to a typical above ground carbon steel tank, most coatings are going to be fairly similar. Obviously, the goal is UV and corrosion protection, protecting it from the sun and for rain and things like that. And there's one type of tank that I want to take just a second to talk about for underground tanks, and that's my own personal recommendation of the best of both worlds with a steel and fiberglass combo. So if you have an underground application and you have an opportunity to design the tank with a steel inner and a fiberglass outer, it's really the best of both worlds because the fiberglass outer is going to negate any of the environmental corrosion concerns for interacting with the soil and the backfill. But the inner carbon steel tank is going to be very compatible with the fuel additives and the fuel itself going forward, and also provides that structural stability. So it gives you a nice small footprint, and I think is a great option if you're designing an underground direct burial application. Now it's important that before we move on from tank design, we take a look at one more type of tank, and that's the day tank or the belly tank that's located at the generator. Now, this tank doesn't necessarily affect as much of the fuel over its life, but even though most of the fuel is not stored here, there is something that makes this very critical to the discussion of fuel oil quality. And that's because this tank is going to see many more cycles on it than the bulk storage tank will in a centralized fuel supply system. So for every time the main tank needs to be replenished, fuel is drawn down, the day tanks at the generator may be cycling many, many times. And every time this tank is cycled, we're going to get fresh air being pulled in above the fuel, and we're going to be having temperature changes on the fuel itself, and all of those lead to things like condensate forming within the headspace of the tank. And so it's important to take a look at these tanks and make them part of the conversation. We're talking about how tank design impacts fuel oil quality. One of the things I always recommend when we're talking about tank design at the day tank is that the ability to have return pumps So a return pump on there, as we mentioned before, is going to allow us to circulate the fuel, perform testing, things like that. And if we have a large amount of water or some sort of a thermal issue at the day tank, a return pump typically is going to allow us to address that immediately, to recycle that right back to the bulk storage tank. Also, we want to have a little bit of consideration of where these tanks are located. So if we have a very thermally stable bulk storage tank, let's say underground or inside the building, but we have day tanks that are on the roof, we can also have thermal issues there. In some of our other presentations, we talk about the comparison between standalone day tanks and belly tanks and how the shape is going to affect those. I won't get into that at this time, but those resources are available as well, and we delve into a detailed discussion of how to do day tank design. So rounding up this section, I want to take a look at some of the common value engineering that we see, especially as projects progress. And we see things like removing the tank lining from the scope, which, that can make an impact. We also see things like removing the platform for above ground tanks, and keeping in mind that each one of these is going to have a real impact on the operation of the system. So it may limit the facility's ability to get on top of the tank. If we have a square tank, to see that there's any sort of rainwater collecting on top or corrosion, things that are directly going to affect the tank and the fuel itself. A lot of times we'll see a reduction in the number of fittings in the tank design. This can impact the way the filtration system that we're going to talk about a little bit later does its job, because we want to separate those lines out. And one of the most infamous ones that we see is the loose bolt manway in place of the emergency vent. So the emergency vent is typically located right on top of the tank itself, and it can be spring loaded so that it stays sealed until there's an overpressure situation. One of the value engineering things we see is that being swapped out for the loose bolt manway, which is essentially just a manway where the bolts aren't tightened down. So the weight of the manway holds it down, and then if there is an overpressure on the tank, that then lifts and allows that pressure to be relieved. One thing I will caution, though, in a lot of cases we can have an overzealous facilities person that sees loose bolts and thinks they should be tight bolts. And now a loose bolt manway becomes just a regular manway, and we no longer have emergency protection for overpressure on the tank. So keep in mind, for every value engineering choice, those can have a real impact on the design. All right. So finally, let's take a closer look at some of the factors that are affecting the fuel oil quality. So diesel fuel is an organic product that begins to decay as soon as it is refined. I know a lot of times we think of fuel like a piece of steel or something that's just sitting there and it's going to be the same when I walk back a few months later, but really there's a lot going on in that tank. Now, the biggest impact is the water that enters the tank. And any tank is going to have an operating vent. And in that operating vent, you're going to get moisture through condensation. So even if the delivery of fuel is very good, very clean, water is still always going to be entering into the tank. Now, sludge formation is an organic process that is made much worse by water, because these microbes actually live in the water and they feed on the fuel, and their byproduct is the sludge that clogs the system. So when we have water in the tank, that's going to make this problem much worse. And as I mentioned before, the composition of the fuel can affect that as well. When we have things like lower sulfur fuel, we're seeing that the antimicrobial properties of the sulfur were pretty important. And so now a lot of these microbes are more active. So taking a look at where this happens in the tank, we know that the fuel is lighter than water. So the water collects down at the bottom of the tank, and the sludge growth is going to happen at that fuel-water boundary. Because the water and sludge content are so important to the quality of the fuel, it's why I refer to filtration as really polishing, because we're not just concerned with any sort of particulate that collects in the tank, but we're concerned about this water content and sludge buildup. And with this water building up, typically weekly generator tests are not going to be enough to just consume the fuel and keep it turned over and fresh. Now, as we mentioned before, the health of the fuel and the health of the tank are really interlinked. And when we have fuel that is having issues, the tank is going to have issues as well, like corrosion. Now, it isn't just about having a rusty tank, which is also an issue, but there can actually be a symbiotic relationship between internal corrosion and sludge formation. As we get little pits and pockets on the inside of that tank surface, those are going to be breeding grounds for these bacteria, which can have acidic byproducts, which are then in turn going to attack the interior of the tank as well. And it can be hard to predict what that's going to do. Obviously, any sort of byproducts like that on a carbon steel tank are going to start attacking the metal. It's hard to say what those are going to do on the different resin formulas for the interior of fiberglass tanks also. So what do we do about it? We know that pretty much every tank is going to have water in it to some degree. And we know that we have to do something to mitigate that. Well, the first thing that we do is we try to look at what is the quality of the fuel that's in the tank at a facility. So on the operations side, we can determine the quality with different laboratory testing and things like that. Obviously, looking at the fuel, if we can observe the fuel in the tank, or if we have a transfer pump set, sometimes I'll take a look at the fuel in the strainers on the suction side, and we can look at how the system performs. Are we seeing high suction vacuum? What are the pressures and flow rates and things like that? Obviously, if we have metal in the oil or something that could tell us that we're getting wear on some of our transfer equipment. And NFPA does give us a little bit of guidance on recommendations to mitigate some of these issues. So keep the tanks as full as possible. We know that a lot of the water is going to enter the tank through the headspace. So if we have a tank that's half full, that's 50% of that tank is headspace that's made up of air that has some sort of water content in it. And that condensate can make its way into the fuel. If we have a tank that's completely full, that's less headspace that we have to worry about. We want to mitigate temperature variations and a lot of things that we talked about. So these are general recommendations from the NFPA. But there is one important thing that I want to bring out, especially when we're talking about water content, and that is dispersion is not removal. So when we're looking to limit or eliminate the water content in the fuel, a lot of times one of the go-tos for a facility, especially if at the design phase we didn't incorporate things like water removal system or fuel polishing, is to go to additives. And one of the common additives that we see for fuel treatment is something which is kind of akin to dry gas, if you've seen that commercial product for your car. And what it doesn't do is turn water into fuel. What it actually does a lot of times is disperses the water throughout the fuel so that the generator engine doesn't see a slug of water coming in at any time, which we know would be a bad thing. The problem is the side effect of dispersing water is that it's now spread throughout the system. And in the picture on the screen here, you can see it appears to be a bad cup of orange juice, but what it actually is fuel with water evenly distributed throughout it. So in this case, the additive is doing its job very, very well. The problem is we've gone from a situation where the sludge is being formed at that water fuel boundary at the bottom of the tank to now sludge is being formed around every tiny water droplet throughout the entire system. So not only is the surface area exponentially larger, but we don't just have this happening in a bulk storage tank where it can be addressed directly. We have this happening in piping, in fittings, in transfer pumps. And we've seen instances in the field where this sludge formation has required not only the removal of valves and fittings and things like that, but the piping itself, because it was so full of sludge due to a water problem and water being dispersed throughout the system. So keep in mind that's not necessarily the best go-to. The best way to maintain fuel quality and limit the amount of fuel water in the fuel is through a fuel polishing system. And having that system designed to be standalone at the facility rather than relying on the facility to call in a mobile service later is going to be the best way to ensure at the design phase that this system is set up for fuel quality long term. In a system like this, we're typically going to want to see at a minimum a circulating pump, and before that pump we're going to have a strainer. Now the strainer is a very low pressure drop device that really is in there just to protect the circulating pump itself. After the circulating pump, we're going to see the different steps to maintain fuel quality. And that's going to include some sort of primary filtration. And very importantly, there needs to be a stage, whether it's a centrifuge style or some sort of coalescing device, that's designed to bring that water out of the fuel. So you may have water that's mixed in with the fuel as it's pulled into the polishing unit. We want to make sure that we're bringing that out of the fuel, separating it so that it can be removed. And then sometimes there'll be some sort of secondary filtration depending on the requirements that may bring that down even as small as 2 microns. But really the most important step here is to remove the water that's driving this sludge formation. And it's important to understand that these fuel filtration or polishing units are critical pieces of the system, and they should be installed on their own piping loop. So as we saw in a previous slide, all of the water and particulate and sludge lives down at the bottom of the tank. When we're designing the connections on a tank, we'll typically have the transfer pump set that's sending fuel to the generator. That drop tube will be up off the bottom of the tank because we don't want to pull the water and the worst part of the fuel. The fuel filtration, however, should have a drop tube that goes all the way down to the bottom. And there's a couple of different ways to do that. I've seen contractors measure the drop tube by putting it into the tank, cutting the end of it at a 45 so that it nearly rests right on the bottom, but can still pull fuel. And really what we want to ensure is that we're getting as low as possible, and then we can access the water and the sludge to remove that from the system. It's also important to understand how the sequence of operation is going to work on these. We can have a PLC set up so that it can communicate with the transfer pump set so that it's not running at the same time that there's a call for emergency power, things like that. And typically these are going to be sized to polish a certain volume of fuel within a certain period of time. So there may be a requirement where the facility wants to polish one of their tanks completely within a certain shift so that one person can be responsible for initiating and then ending the process. But it can also be set up to run automatically as well any time of the day or week. Now, we talked a lot about water, and I think that's really one of the more important impacts, especially with things like ultra-low sulfur diesel. But some of the other issues that can happen to the fuel within the tank that we alluded to before are thermal issues. And I'm going to start with coal fuel because I'm located here in the Northeast, and this is something that we run into quite a bit and have for a very long time. And when we're looking at diesel or number 2, they're typically going to have a cloud point of about 32 degrees Fahrenheit. And the cloud point is when some of these paraffin waxes start dropping out of the solution, out of the diesel, and so you're going to get tiny little bits of wax. Those are going to impact things like filters. So if we're at our cloud point at 32 degrees or so, we can start seeing a higher pressure drop across filters and things like that. As we go lower in temperature, typically around 15 degrees for diesel, we're going to start reaching our gel point. And this is when the overall viscosity of the fuel changes. And that's going to have a larger impact on things like valves and transfer pumps. Now, of course, we can do things like switch to a winter blend. There are some options on the fuel composition side, but it's not necessarily a cure-all. All it's really doing is pushing those temperatures a bit lower. So what do we do then? Well, we need to add some BTUs into the system. And the use of in-tank heaters is a good idea, depending on where the tank is located. We talked about above ground versus below ground. It's important to understand, though, that if we're going to use an in-tank heater, we also want to have a way to keep those BTUs from directly leaving the tank. So if the tank is above ground outside, it may also be important to insulate the tank so that that in-tank heater has a chance to catch up. Heat trace is an option for piping, but that's generally not going to be a good way to inject a lot of BTUs into the system. It generally is more going to be geared towards maintaining the temperature of fuel as it's transferred from one area to another. Now, one way that is very effective that I recommend is having some sort of an electric heater located at the transfer pump set. And the reason that this is effective is if we have a main tank and a generator day tank that both need to be maintained as far as heat, we can put temperature sensors in those, and even an outdoor air temperature sensor as a feed forward into the system to preemptively maintain the temperature of the fuel. And if we have a three-way valve that allows us to either recirculate with the main tank or then to circulate fuel with the generator tank, we now have a heater in one location that can maintain the fuel temperature at multiple locations throughout the system. So if the main tank needs to be elevated in temperature, we can change the position of the three-way valve, recirculate with the main tank, bring that up, and it also heat the fuel throughout the transfer piping. And then the three-way valve would then alternate to allow us to supply fuel up to the generator tank and maintain the fuel temperature there while supplying warm fuel throughout the transfer piping as well. So that can be a very effective configuration depending on the application. Something that we've seen for a long time in different markets like in Southern California, other southern states here in the US, but we're actually seeing a lot more of here in the Northeast is heat issues, especially at the generator day tank. So one thing that we're noticing is that a lot of these generator systems are not only circulating more fuel than they're burning, but they're also returning it at a very high temperature. And this can pose some problems, especially if we're in an area where we're limited on the size of the tank that can go at the generator. So if we have a large generator and a very small tank, we're circulating a lot of hot fuel back to that tank. We can have problems where we're going to trip out on high inlet fuel eventually. And also, it's just not a good idea to elevate the temperature of the diesel. It'll be interacting with things like its flash point and can be a real problem. So what do we do about it? Well, we see some systems where we have things like a radiator or a tank fuel cooler, and that's certainly an option. And one thing that I always recommend, as I mentioned before, with having a return pump on the system, this is a great option to take an amount of over temperature fuel and immediately swap that out with cold fuel from the main tank. And it's going to be along with all those other benefits that we mentioned earlier. And at the very minimum, it's always a good idea to have some sort of temperature sensing in the generator tank and the main tank so that we even know that these issues exist. Sometimes they're not anticipated, but having an ability to measure those temperatures is going to be very critical to troubleshooting down the road. One more thing that I want to look at as it relates to high temperature fuel, and it's a solution that we've seen in the past, whether a retrofit or on a new design, and I want to talk about how that can impact the fuel oil system design overall. So a typical piping arrangement is going to have the supply and return from the emergency generator, as shown in the top right in blue, going directly to the day tank itself, or sub-base tank or belly tank. And then you'll see we have the supply and return from the main tank coming into the other side of that day tank. Now, this is the typical setup, and if that day tank is very small and we're recirculating a lot of fuel from that emergency generator and returning hot fuel, that can have an issue, as we mentioned, with over temperature fuel in that tank. We've seen an alternate piping arrangement here on the next slide where the return from the generator goes all the way back to the main tank. Now, on the surface, this is a great solution, right? We're not sending any fuel back to that small day tank at an elevated temperature, so issue solved. The problem comes in, though, if this is a retrofit. So we're seeing generators replaced, the rest of the fuel system staying the same, and we are now changing that return from the generator to go back to the main tank. We're not sized at our transfer pump, our piping, our valves, and our day tank for the burn rate now of the generator. We're sized for the flow rate of the onboard generator pump. So you may have a situation where we have, say it's a 1 megawatt generator, 1000 kW. We say, well, we're burning, let's say, typically 70 gallons per hour with that. And so for a 2-hour sized day tank, we got a 140 gallon tank. But if we send the excess fuel that's being pumped through that emergency generator all the way back to the main tank, that changes the math, because that generator could be flowing 2 to 3 times as much fuel as it's burning through the generator, and all of that goes right back to the main tank. The other issue is, let's say we're at the design phase and we say, well, high temperature fuel is a concern. we're going to go ahead and resize all of the piping and the tank and the transfer pump to accommodate for that higher flow rate. What we've seen in the past is that it may be very hard to determine what that flow rate is early on in the design process or even at the submittal phase. Many times in the generator submittal, it's not clear what the actual flow rate is of the onboard pump. And so now not only are we upsizing everything for that larger factor, but we're also factoring in an additional safety factor because of uncertainty. So we have a system that's upsized quite a bit to accommodate. All right. I appreciate your time. Thank you for listening and viewing our webinar on the different ways that tank design and fuel quality is impacted. I appreciate you joining us, and we're going to be taking some questions here in a minute, and I look forward to interacting with you on those. Thank you very much.